Okay.
We have 1 minute to go, sir. Another 1 minute will start, sir.
Professor Raghuvanshi from Bhopal is there. Again.
That's why I told you, sir. Datta sir, good evening.
Namaskar, Raghuvanshi ji. He's classmate of Ghanshyam Konade.
Hello.
Namaskar. It's a new subject, Raghuvanshi sir.
No, it's not new. It's 62 years old.
only Pangale and Suresh Pandey and Bhavesh do it, and Malhotra from MECL.
I am only 1 year elder to this particular subject, 62, so I'm 63.
From
We have
Suresh
36
Pandey.
participants. May I now request our Jadwanda Das ji to get started now? I think this is time.
Sir.
Yes.
Good evening and namaskar. Warm welcome to all of you. And to begin with, I welcome our President, Dr. Omkarnath Mohanty, and Vice President, Sujit Kumar Mohanty, and the most distinguished member of SGAT and today's speaker, Dr. Bhavesh Sarkar. And for the information of all, this is a kind of a unique program which actually a brainchild of our President, Dr. Omkarnath Mohanty, where we thought that we will be inviting the members of the SGAT. We have huge number of members all across India, and even we have international members. So we thought of using this, the like members having a lot of expertise to share their knowledge, not in the form of actually talk. It is more of a kind of a participatory or interactive or some kind of a discussion where the domain experts would be speaking, and then he will be joined by the similar domain expert among our fraternity, and then we'll have some kind of deliberation and brainstorming, and maybe we clarify our own doubts and problems. And in the process, the audience who would be attending will be also benefited. So just to tell you that we have a very prestigious program that is known as DLS, that is Distinguished Lecture Series, which in fact is done by invitation, where the very, very eminent across the globe, the scientists are invited to speak. So that's a different. But here it is purely the members of the SGAT who would be sharing their knowledge and expertise. With this, I would now request our Vice President, Mr. Sujit Mohanty. He would introduce our speaker and will begin the talk. Mr. Sujit Mohanty, sir.
Thank you, Mr. Das. It's really a great pleasure on my part to introduce such a big personality, Professor Bhavesh Sarkar, to whom I have been knowing since long. And he is a person of repute, particularly in the space of geostatistics in India and abroad. Professor Bhavesh Chandra Sarkar, professor in the Department of Applied Geology at IIT ISM Dhanbad, is a renowned geostatistician possessing over 4 decades of professional experience with a strong blend of industry and academics. He obtained his MSc degree in Applied Geology from IIT Kharagpur in the year 1980 and PhD in Mining Geostatistics and DIC in Mineral Resources Engineering from Imperial College of Science and Technology, University of London in the year 1988. He served MECL during 1980-81 and Hindustan Zinc Limited during 1981 to 1989 as geologist and senior geologist. He joined ISM as faculty member in December 1989 in the Department of Applied Geology. He spearheaded the Department of Applied Geology as its head during 2010 to 2012 and the Department of Civil Engineering as its founder head during 2013 to 2014 at IIT ISM Dhanbad. As director of AICTE, New Delhi, during 1997-98, Professor Sarkar contributed towards planning and policy formulation of technical education in the country. He is a recipient of a large number of awards in recognition of his impeccable professional career and outstanding contributions in the fields of mineral exploration and geostatistics. I am really privileged to name a few for the knowledge of our distinguished participants. Professor Sarkar is a National Geoscience Awardee for the year 2019 in the field of applied geology for his significant contributions in the field of geostatistics and IT applications in mineral exploration. He is also the Distinguished Alumnus Awardee of IIT Kharagpur for the year 2020, MEAI Service Excellence Award for the year 2021, Information Technology Award of MEAI SRG for the year 2018-19, SGAT Award of Excellence for the year 2014, Dr. J. Coggin Brown Memorial Gold Medal Award of MGMI for the year 2014-15, S. Narayana Swamy Award 2014 Geological Society of India, Distinguished Academic Award of IGC for the year 2013, etc., etc. Professor Sarkar represents various committees as expert member, both in India and abroad, including National Mineral Exploration Trust and Geoscience Advisory Council under Ministry of Mines, Government of India, and expert committees of Science and Engineering Research Board, Department of Science and Technology, Government of India. Professor Sarkar, to his credit, has over 120 research publications in journals of repute and a total of 8 books and a book volume. He has authored the book titled Essentials of Mineral Exploration and Evaluation, along with Dr. S.M. Gandhi, published by Elsevier, USA in June 2016. He is a council member of MGMI and MEAI, Vice President of the Indian Geological Congress, Chairman MEAI Dhanbad Chapter, and also a life member of SGAT. With this, now it's my proud privilege to invite Professor Sarkar to start the presentation. Professor Sarkar, please.
Thank you so much, Sujit. Rather, it was bit exaggerated, so much introduction. So, which I'm sure I'm a very small man by my height as well as by my stature in front of very noble persons. What I can find in front of me. In fact, the president, Professor Omkar Mahanti, was my teacher at IIT Kharagpur. If you remember, I was there a student in the art hall at that point of time. And once upon a time, before we start, let me just give you one small instance. In 2014, when I was receiving SGAT Award of Excellence, in fact, the 3 persons who were on the stage, because was Professor Omkar Mahanti, the chief guest of the function was my junior from IIT Kharagpur from electrical engineering, from Tata Steel, Mr. Arun Misra, who is now the CEO of Vedanta, and of course myself. So these 3 were from IIT Kharagpur, standing in the same platform on that particular day. So with this, I can find Abani Ranjan Samuel is also here, my ex-student from ISM Dhanbad. Is must be quite early for you now, is it so?
Yes, 7 o'clock, sir. 7 o'clock. 7 morning.
In the morning, right? So
7 in the morning. Okay.
With this, let me start my talk about, because I would not like to make it a more of elaboration, but I found that, well, let me try to share whatever I happen to know with august body like SGAT. And this is what I thought that let me take you through some of the, why we use geostatistics, what is the utility of geostatistics, because I used to find there was during 1950s, there was a journal known as, it came out in some journal who took out economic from economic geology. That was the title of the paper in economic geology. Similarly, I would like to emphasize on my talk who took out geo from geostatistics. Otherwise, people think that it is simply statistics applied to geological data, which is absolutely wrong. So let us take it out from our mind. Yes, of course, the fundamental aspects are borrowed from statistics, from the definition of random function, random variables. But yes, we will use that. Random function is the basic understanding of all these autocorrelation functions. So we'll start. Can I share my screen now?
Yeah, you can say.
Yeah, please go ahead. Please go ahead.
Okay.
And before he starts, I would request all our guests who are attending this, kindly mute your audio and if possible your video during the talk when Bhavesh Sarkar will be speaking, to give him a chance to have an uninterrupted talk. Thank you all.
Thank you so much. Is my screen visible?
Yes.
It is visible, but you have to slide. You have to make it slideshow mode. Okay, fine.
No, that's okay. I mean,
Right.
visible or not? That's what.
Yes, yes.
Yes.
Visible.
Yes.
Okay. So this is the title of the talk, which you already know about it: Geostatistics in Exploration and Mining. Because as read out from my CV, what Sujit had read out, because I hold a degree both in applied geology as well as also in mining engineering from Imperial College. So, but that part was only mining geostatistics. Let us have a small, go through to what is the role of geostatistics in the exploration and mining value chain. That is the very first thing that one would like to know. In fact, is it something out of the way? Does it have any relevance?
Yes.
Sorry, any queries, please? No.
Okay, carry on. Somebody had unmuted. I had muted him.
Okay.
No, sir.
So-
Please go ahead.
So when actually this particular subject, it got into a subject, the techniques got into a subject. That was the formal year of this techniques getting into the subject was 1960. So the developmental aspects of geostatistics started from 1960. But nevertheless, the work started much before that. So I'm going to tell all the names and all those, but the two pioneers in this particular field, I'm going to name them, show their photographs. So for efficient exploration and mining, one needs to know the distribution of grades and tonnages within mineral deposit. That's our basic understanding. Now, do we say that geostatistics is only applicable for exploration and mining? Definitely not, because it is altogether a subject by itself based on the theory of regionalized variables. And the practical applications of regionalized variables, what Professor Mathurin named it in 1960 was geostatistics. So as we go about, geostatistics is defined as a group of techniques based on variography, and many of us would call it semi-variography. The reason I'll tell you later. To describe the variables with a spatial component, whatever could be the variables, right? It could be grade, it could be tonnage, it could be bulk density, it could be hardness, it could be anything that we can think about, provided it is defined as a regionalized variable. And this particular role has become increasingly important throughout the mineral extractive industry. It started as a linear geostatistics in linear form, and today we are where, that is what I'm going to show you a few of the slides after this. Two of the purposes of geostatistics is to produce estimates and simulation of the mineral deposits. The very definition of this English word estimates is to provide a value which is close to the reality, but not exact. It can never be exact. Any estimation techniques or any other simulation techniques will provide us a value from the surrounding sample values very close to that. Never ever it will be exact to that. Coincidentally, it could be, but otherwise it will never be exact value. And I'll use a particular term later on where we tell, can you tell me the exact value of this block? So it's something we'll discuss about it. So this robust estimation of grade and tonnage is key to energy efficient mining and exploration. We have the methodologies which have been evolving and being developed right from 1960. This is 2022. And even now, 2022, where geostatistics lies, that is what I'm going to share with you. Right? Application of the new estimation techniques, estimation of non-traditional variables, analysis of how the change in inputs affects the final result, and incorporating the most important part where I emphasize on this one, the very first thing, incorporating geological information into geostatistical practice. Many of us forget, as we go ahead, we tend to forget the geology and try to make it through a computer software, which is incorrect, and probably it could be disastrous. Okay, so now let me let me show you some of this. Let me see, does it write my pen? Yeah, it writes. So I was practicing that. Don't worry about this. Let me erase it out. Okay, right. So what is geostatistics and how it is different from ordinary statistics? This particular example I always follow in a simple manner wherever I go, including with my students. Just think of 5 values, 1, 2, 3, 4, 5. And of these 5 values, supposing we provide a spatial arrangement and we consider the arrangement number 1 as first arrangement and arrangement number 2 as the last arrangement, and calling it arrangement number 1 as the most ordered arrangement and arrangement number 2 is the most disordered arrangement. If we apply classical statistics, which does not take into account of the spatial positions of the samples locations or the value locations, then what happens? We only get the mean, variance, whatever may be the arrangement of these 2 arrays of the most ordered and most disordered. Please remember, we have 5 samples. So how many arrangements can be there? Special arrangements? 5 factorial. That is 5 into 4 into 3 into 2. That is 120. So in between these 2 arrays, arrangements, spatial arrangements, array 1 and array 2, we have another 118 spatial arrangements. That makes up. Could you mute, please? Anyway, so if we look at the spatial arrangement 1 and spatial arrangement 2, both have, using classical statistics, has a mean of 3. And what is most important over here, that is I'm going to show you the variance or the standard deviation. Variance is 2.50 in both the cases, or in all the 120 cases, because there will be 120 spatial arrangements, right? Standard deviation, of course, it is square root of the variance. Now, if I bring into the concept that I have an arrow over here shown on the left-hand side, shown by the red arrow. So this red arrow, if I place it in between the 50% distance between 1 and 2, if this is my spatial arrangement, if I consider arrangement number 1, most likely you will tell me the value at this particular position is, okay, let me point out, value at this location point P1 would be something. You will say from your, you will apply your mind and you tell me that it will be 1.5. Am I correct? Yes, the value could be 1.5, most likely. Whereas for the same location, arrangement number 2, I get, let's say, most likely value as 2.5. I have not played any magic. My name is BC Sarkar, not PC Sarkar. I have not played any magic. Is it so? The same position, but the values are changing. So the very concept of spatial positions has to be brought in. Ordinary statistics has no way to tell me this particular value at this location. Similarly, we take another location on the right hand side of sample 4 on the arrangement number 1. Most likely you will say that this is now 25%, so it is now 4.25, right? And most likely over here you will say in between this is something like 2. I mean, or maybe slightly about the 2. Why it is happening? The very concept that we have in our mind of the spatial positions. If the spatial positions play a very vital role, and in order to that, I get the value, otherwise I'll never be able to say that which value is close to another value, next value, or which value is at a distance from another value. Classical statistics has no way to resolve this particular aspect. Whereas this particular subject, geostatistics, in other words, I call it, the name geostatistics was coined by Professor Mathurin. The broad family name is spatial statistics. That means the space component has come in. Is it really only space? No. Time and space. So we call it spatio-temporal phenomena. So anything, it could be in terms of time, it could be in terms of the space, it could be in terms of a combination of both, spatio-temporal. So now if we consider the spatial variance over here, S squared delta H, that means sample to sample variance, if I calculate, it comes out as 0.5. How it is that 0.5? Because here I use a particular expression which takes into account, because you see the normal ordinary variance, I said 1 upon n minus 1, summation of x minus x bar square. Whereas spatial variance will be taken into account of 1 by, this is number of pairs, summation of not x minus x bar, that means not the individual difference from the mean, but rather I would bring in some more a variable known as zx and zx plus h. That means the same, where h can vary from 1 to n, right? Whatever may be the spacing. Maybe if this spacing is, let us say, for example, it is 10 meter. So all this h is equal to 10 meter, multiple of 10, 20 meter. So when one is compared with this through this formula, then as you go ahead, this is that h is equal to 1, h is equal to 2, and so on, makes a pair. So you calculate for every spatial arrangements, right? This value that we have got, this for the first one, that is for the first one, right? If I go on 1 minus 2, 2 minus 3, 3 minus 4, 4 minus 5, right? I will get a value of 0.50. And if I go to the most disordered one, I get a value of 4.37. See the variations, right? This spatial variation must be reflected in order to show how the samples are related with one another in every arrangement. And that is taken into account in this particular spatial statistics. That's the difference, major difference between statistics and geostatistics. So this subject, what we have discussed a bit till now, is basically a set of probabilistic methods that provide spatial models for correlated random variables. Now, correlated random variables, so I'm using the particular term known as random variable, a variable that can take up any value by chance experiment. So when I say correlated random variable, in my previous slide, I had said that one is correlated to 2 over a particular distance of separation, which is called the lag distance. 2 is separated with 3, 2 is related to 3 by that one. So what's the total relations? How the samples are correlated with one another in terms of the increasing distance of lag or lag distance, how they behave. So initially what will happen? That the values when h is equal to 0, that means, in other words, the same set of values is being compared to itself. And this particular function is what is called the most important one, autocorrelation. That is correlating the same series by itself over different space of lag distance. Autocorrelation function. In fact, the next term that I'll be using in my next slide or one slide after will be a semi-variogram. This particular autocorrelation function that we use is a semi-variogram function. Now, a spatial model, as I said earlier also in another slide, can be an estimation model and a simulation model. I'll be deliberating on this throughout my talk, right? Simulation, of course, it will come later on, a bit of it. And then, of course, I'll be touching on what is the latest in geostatistics. That's what I call it machine learning geostatistics, AI geostatistics. So it explains the spatial relationships amongst the sample values, theory of regionalized variables, based on the theory of regionalized variables. If I just now I said, what is a random variable? A variable that can take up any value through chance experiment, no question of any spatial relationship or temporal relationships. Regionalized variable is a variable that is related to its position in space. Exactly the one that I've made in my previous slide is related to its position in space. And the second condition is also the same condition with our random variable, that it must have a constant support. Constant support means over what distance, right? What is the support of the samples? It could be in terms of 1 dimension, it could be in terms of a 2 dimension, it could be in terms of a 3 dimension. 1 dimension means what is like along, it's a line, right? So length of the sample. What is the length of the sample? Suppose I take one sample of 2 meters, another sample of 5 meters. No, I can't play statistics, I can't play geostatistics. It has to be of the equal support means equal length. Similarly, in 2 dimension, equal area. In 3 dimension, it will be the equal volume. Ultimately, we'll all work in the 3 dimension. We start our imagination and understanding process from 1 dimension. So, development of geostatistics emerged in France in the early 60s from the work of Professor Georges Mathurin, which was based on the original studies made by Professor D.G. Krieg concerning optimal assigning of weights to neighboring samples used for estimating block values of gold mines of South Africa, later on extended to diamond mines of South Africa. I don't know why this pen symbols are coming out to see that. Now it is, this is, a pic of Professor Georges Mathurin, who is known as the father of geostatistics. So Professor Mathurin, right from 1930 to 2000, right, is a total period, right? He had built the major concept of the theory of estimating resources and named it as geostatistics. And he named the estimating geostatistical estimation technique as Krieging in the honor of Professor D.G. Krieg, based upon his early empirical works carried out. So Professor Krieg should be given primarily the full appreciation for developing this subject. Professor Krieg was basically a mining engineer, a professor in University of Witwatersrand, Johannesburg, professor of mineral economics, and he was of course a British, but living over there. But then I had the opportunity to meet him all 3 years. I was at Imperial College from 1985 to 1988 during my PhD research. All 3 years he used to come and give us a lecture there. I had that opportunity. So this particular fundamental classical Fraternity geostatistics applique, which came up in 62, 63, which defines the fundamental tools of geostatistics in terms of basically, which deals with semi-variography, variance of estimation, and spatial dispersion, and Krieging. Please remember, Krieging, which Professor Mathurin had termed it, in the honor of Professor D.G. Krieg, many of us in India, we have a tendency to write the spelling of Krieging as double G. And as a professor, I give him totally 0 marks. If in one sentence, if I find, or if I find a paper coming to me for evaluation, I reject the paper because he doesn't know the name of the technique under whose honor the name was given. Right, now let me tell you one thing. Many developments in mathematical geological modeling are now grouped under heading of geostatistics. We have fractal geostatistics. We have so many terms known as geostatistics. Fractal, fractional dimensional analysis, right? Fractals and chaos, maybe many of us may be knowing it. So now we are dealing in the geostatistics, fractal dimensioning. So as I already mentioned over here, the regionalized variable is viewed as a realization of a random function, which is a collection of random variables. Here, I must let you know what is a random function. Many of us may be confusing between what is called a random function and random variable. No, random function is a probabilistic description of spatial distribution of a variable. It can be thought of a collection of correlated random variable or dependent random variable or regionalized variable. Or with the same breath, it can be also be thought of independent random variable, which is values as functions rather than the numbers. So this is what we must also see, that whether we understand this particular random function. And here I will use another particular term known as what is called your stationary random function. So there are certain stationarity hypotheses which has to be added to, which has to be understood, and then only your theory of regionalized variables will be applicable, otherwise not. Geostatistics has been applied to geology and mining since 50s, natural phenomena since 70s. And I will tell you, it started with mineral deposits, but later on it went up to this petroleum geostatistics in a big way. All these petroleum companies throughout the world are using it in a big way. I can tell you, they use it many a times through a software, what is known as Petrel. And it got reintegrated mainstream statistics during 1990s. Today is 2022. This is Professor D.J. Krieg, and my salute to him, what he in fact coined it. Otherwise, this subject won't have come, right? So basically, this few things, semi-variogram, Kriegging, conditional simulation, all this, right? It came up. But Professor Krieg, he had thoroughly warned that technique should not be misused. There are many of us misuse the technique, and at the end of the day, we say geostatistics does not produce results, which I'm not able to accept it. Right. If I have a look at what is this particular developmental aspects from 40s to 50s, the development of autocorrelation theory and its various applications. This just it can have an overlap, right? This is a broad duration that I've been showing you. So 40 to 50 autocorrelation, 50 to 60 regionalized variable theory, 60 to 70 linear geostatistics, 70 to 80 nonlinear geostatistics, 80 to 90 non-parametric geostatistics, 90 to 2010 geostatistical simulation, 2000 to 2010 and still going on strong multi-point geostatistics based on the training images, not based on the semi-variogram. 2010 to date, machine learning geostatistics. So we have come to this particular stage where we have what is called AI geostatistics. And one of my recent publication in 2022, month of June, was on machine learning geostatistics in one of the Q1 journal, what is called neural computing applications. So these are all the stories and all those, but I would like to say the geostatistical methods utilize an understanding of the interrelationships of the sample values within a mineral deposit and provide a basis for quantifying geological concepts of inherent characteristics of deposit or ore body being modeled. That means whatever the characteristics of the body, these are spelled out. Second, very important, change in the continuity of interdependence of the sample values according to the spatial trend of the mineralization. Third, range of influence of the interdependence of sample values along various directions. It can be different. And if it is different, then we have another terminology which I'll discuss very soon. So based on this quantification, geostatistics is able to provide me with an estimation with minimum variance and an error associated with that estimation, both on a local and as well as a global scale. Today, what we have geostatistics, what started actually with our mineral deposits, all right, in mineral exploration. So we have geostatistics in mineral exploration, petroleum exploration, coal exploration, hydrogeology, mine planning, geotechnical engineering is one of the another important area which is coming up, right? Like in this assessment of your stability. Geostatistics and environmental studies heavily used. And lastly, what is called the trendy geostatistics, amongst many others, many others. Even let me tell you, even the stock market has used geostatistics. The moment I say geostatistics, it is basically, you must remember, spatial statistics, theory of regionalized variable to forecast the future trend in stock market. It has been used. Geostatistics is not only used in mineral estimation stage, but also in other areas of exploration and mining, as I've listed over here. These are only few. In establishing the mineralized limits, where you have a very disseminated ore body, it has to be, the mineralized limits has to be set in selection for a cut-off grade. The deposits which are highly variable, it needs a particular, right, selection of an optimum cut-off grade. But to go ahead with a selection of an optimum cut-off grade itself is dynamic. It can never remain static. It can remain static, but with changing scenarios, we must estimate the reserves with different cut-off grades. Resource reserve classification, optimization of drill hole spacing, various stages of mine planning and design, grade control plan, among many others. We'll go quickly, slightly, right? Particularly, what is the particular first autocorrelation function that I've been talking about? The word term I'm using semi-variogram because it is half the variogram function, and I'm going to show you what is the variogram function. This is variogram function, the first one. If zxi be the value of a sample taken at position xi, that as I showed you in one of my slide, no? Where I was explaining the two arrangements, most ordered alignment. The very first location is zxi. The second location is zxi plus h, separated by the distance h. Right? In one dimension, in two dimension, and in, of course, in three dimension. Right? So what we deal with basically three-dimensional scenarios. Right? So the first formula that I've used, expression that I've used, is twice gamma h is equal to 1 upon n summation of zxi minus zxi plus h whole square. This does, you know, when I correlate it with another term known as covariance and ordinary statistical variance, this particular gamma h term. So the sum total of the gamma h plus the covariance, that is spatial. So we write over here gamma h plus the covariance. This means the degree of similarity. This means the degree of dissimilarity. So when h is equal to 0, what would be your dissimilarity? 0. So as h increases, so this is my h axis, this is my gamma h axis. As h increases, the dissimilarities will increase. So initially it will be 0, and then it will increase. Then depends upon what the trend goes. After then, sometimes it flattens, sometimes it doesn't flatten, right? Sometimes it continues, whatever. But if I say that this is my statistical variance line, that is a square, which is not a function of h, right? And if this is my gamma h curve, and I have also, through this equation, sum total of the dissimilarity and the similarity is equal to the statistical variance. So if I write that this is my statistic, the gamma h at this particular 1h, at this particular 2h, this is my magnitude of gamma h, this is my magnitude of CVH. Look at, when h is equal to 0, the dissimilarity is minimum, 0, and degree of similarity is maximum. As h increases, the degree of dissimilarity increases and the degree of similarity decreases at this. Can you see at this particular point, the entire magnitude is gamma h, the CVH covariance h is equal to 0. So that is why we use gamma h, half the semi-variogram function, which is expressed by the second expression that I've given over here. This is the basic understanding how it is paired up at 1h. This is at 1h, right? This one at 1h, this one at 2h, this is at 3h, this is at 4h. So for these few samples, right, 5 samples, I can go maximum up to 4h lag. So this is the one that I was showing you in my previous slide, right? The trend of the semi-variogram, the trend of the covariogram, and the sum total at a particular component, at a particular age value, the sum total is your gamma H, right? So this is your gamma H component, this is your covariance component. So this is your covariance curve. As I told you, there is maximum at when H is equal to 0, and it slowly decreases. This one, dissimilarity curve, semi-variogram increases. And the sum total is always given by that is equal to ordinary statistical variance. So can you see over here, the ordinary statistical variance line is a flat one. It is not a function of age. Nothing happens as age increases. There is no impact on the sigma square. So that's the difference between ordinary statistics and geostatistics. Again, the particular properties of this geostatistics, as I told you over here from the semi-variogram, at H is equal to 0, gamma H is essentially equal to 0, the first one. And this, what does this mean? Gamma H computed along one direction, let us say east, is equal to gamma H computed along west. What does that mean? Whether I'm computing in this, suppose this is my east, so this is my west. Whether I'm taking my pair as 20 with 24 or 24 with 20, the value will be same. And gamma H is non-negative. It can never be negative because it's a square term, right? If someone of you are getting a negative value, please go back to your calculations. And now for practical considerations, where we should have values at every grid location, we may not have of the grid. So that is to take care of those, these two tolerances are used, distance tolerance and angular tolerance. And together with it, then there is a spread limit, right? Also associated how much, right? If the characteristics or the phenomena is not similar in all directions, then we'll call it as directional anisotropy, which denotes whether or not the resonance phenomena has greater continuity in a particular direction as compared to the other directions. Let us say along strike direction, if you go, you take a ore body, you take a mineral body, along strike direction you go, what do you expect? You expect there will be less changes. Now, if you go across the dip direction of the deposit, what will you expect? Variability will be higher. So this is the basic concept of geology understanding at it, and it must match with my semi-variogram. Must match. It is nothing like the moment I'm saying it is geostatistics, semi-variography. Let me tell you, mathematics has not, given any formula for, to the nature to form a mineral deposit. Mathematics has not given any formula. So that it has formed by its natural process, whatever may be the ore forming process, it is formed by its natural process, and we have to understand through geology. So that must be our essential ingredient in any other mathematical applications as far if we want to get a good value, an acceptable value. Good value means an acceptable value, acceptable estimated value. So this is what is the directional anisotropy, whether the phenomena is different in different directions. If it is same, we call it isotropic. So this is just to show you in various directions, we compute experimental semi-variogram. Now, it depends upon, again, the whatever is, it is not exactly that you have to go for north, northeast. So this, say, north means 0 degree, this is 45 degree, this is 90 degree, this is 135 degree, isn't it? So automatically by that particular one, I was saying gamma H is equal to gamma minus H. It means actually gamma H computed along one direction is equal to gamma H computed along diametrically opposite direction. So if I compute along 1, 2, 3, 4 direction, I have already computed along this. And the very requirement of controlling over here is that I must compute along at least 4 directions. Normally what happens, I'll tell you. Supposing the major direction of the body is somewhat like this. Let us say the ellipse comes like this. It is an isotropic situation. Okay, I did not draw it correctly. Let me draw it over here. See what happens. Here, this is what is called the range of inference. This is what is called the range of inference. If I take this, let us say there is 10 meter. This is also 10 meter. So if I draw along north and along east, but the axis, major axis of the ellipse is along northeast. So I'll completely miss out the anisotropic behavior. So that is the requirement of at least computing in 4 directions. So automatically means the 4 diametrically opposite directions. That will, the direction of anisotropic could be like this. What would be the isotropic situation? This. These are of course the direction, not. Anisotropic can be like this, like this. This is the major axis, like this, or at any other angle, like this. So one has to be very, very thorough about this, this anisotropism, and one has to bear in mind this particular, because this plays a vital role in selecting those neighboring samples during the process of prigging. If it is like this, let us say, one sample I have here, another sample I have over here, another sample I have over here. Now, suppose this is a point to be estimated. For example, to this point, this sample distance wise it is closer, but this will not be taken into consideration for the purpose of estimation. Whereas this sample is at a distance longer than this one, but it will be taken into account. Can you see the axis of the ellipse? Major axis and the minor axis. So that's the reason. If it is just the reverse, if it is reverse, then of course, again, you have the selection of the samples will be taking place. These are called, I'm not going into the detailed mathematics and all those. I'm just telling you the implications and applications. This is how it is calculated in 1 dimension. The values of gamma 1 at gamma 1 lag, 2nd lag. These are the computations. And as you can see, the values are increasing. So the dissimilarities are increasing. This is in 2 dimensions, right? So this says, when I'm saying in different directions, I'm taking this direction, this direction, this direction, and this direction. So almost it is coming. So I say it is the variable is isotropic. It is almost similar. So this is what is called, when you try to fit a, if I look at the structure, so the correlation, spatial correlation structure with increasing distances, right? These dots are exactly the values which have been computed, and to these values I have fitted a model. But fitting a model, there are plenty of techniques. One has to really exercise through that, right? It is not that easy that I just take a pen and just try to fit a model like this. But for your easy understanding, so let's say I fitted a model, and let's assume the model fits the best, right? Now this distance to which the model, this curve grows and then plateaus off at its this particular value is what is the distance is known as the range of inference. In other words, the distance which is denoted as A, range of inference, is the maximum distance within which the samples are correlated. Can you see that? But beyond this, irrespective of the distance increasing, there is no further correlation. So samples are totally independent in this region. Samples are dependent, or in other words, correlated. And this where the curve actually intersects onto this ordinate, which is the gamma h, the semivariance axis, right? It is the estimate of a particular variance, what is called the nugget variance, or popularly known as nugget effect. This is random component, unexplained component variance. Whereas, can you see from the curve, this is unexplained, this remains, this is not a function of h. This remains, this is the value at this 1h, this is the value, same, right? And this is the component of your, this, what is called the remaining component is not written over here, continuity variance. So the very first thing is my nugget variance where it intersects. But let me tell you this one. If you magnify, as I told you, at h is equal to 0, it is essentially equal to 0. So it will be 0. And this is what is called the short range correlation. Short range, that means below the limit, sampling limit, their effect is there. That particular part, that is what we call for delta h. For very small values of h, we have this term as h tends to 0, but not equal to 0, is equal to the nugget component. And let me tell you, this is one of the most important part for any modeling, nugget effect. If it is wrongly estimated, the total estimation will go wrong. Many of us put more emphasis on the continuity component rather than the nugget effect. And you must know, one must know, understand what are the causes of nugget effect. I call it causes of nugget effect. There are two components. One is a human random component, sampling error, assaying error, instrumental error. All this comes as a nugget effect. And another part is what is called the inherent characteristic of the deposit. For example, let us take an example of a sedimentary copper deposit versus a hydrothermal gold deposit. We understand it geologically. Now tell me the variability, unexplained variability, inherent variability will be more in which deposit? Hydrothermal gold deposit or a sedimentary copper deposit? Geologically, you tell me. Obviously, you say that it will be more in hydrothermal gold deposit, isn't it? Yes, that must be reflected over here in my nugget effect. As the nugget effect increases, let's see over here, as the nugget effect increases, what happens? My continuity component is decreasing because it is that this component, the sum total of the nugget and the continuity is what is called the CIL. See over here, and this is my sigma square, that is the statistical variance. And theoretically, this CIL, when it reaches the CIL, it is equal to a square, but not always. Theoretically equal to, right? So what happens, what I'm trying to show you, as the nugget effect increases, the continuity component increases. That means the explainable part of the variance decreases to that extent when nugget effect is almost the total component and the C component is 0. That means it is a flat like this. That type of radiogram, we call it pure random model. Semi-radiogram model, pure random model, and you cannot apply geostatistics because there is no special correlation. So one has to understand the application of geostatistics. Suppose there is no at all, but again, let me tell you, when our drill hole spacings are quite wide, we do not know in between what are the characteristics. So when you carry out our infill drilling, maybe some structures are there, maybe some correlation is there. That is why we always provide, go ahead with construction of semi-radiogram at all stages of drilling to come out with the inherent correlation, spatial correlation structure. Don't jump to the conclusions. So these are all definitions that I've already gone through. Let me not repeat this. Now, again, one very important thing is that when we construct semi-radiogram, as I was showing you, supposing you have a folded structure, then what happens? Suppose you have a pinch and swell structure. Should I consider this distance between, if this is my ZX and this is my ZX plus H, two samples located at H distance separated, which distance of separation should I take? Whether I should take this H1 or this curved distance H2. Obviously, you will say from your knowledge of geology or your mind application, you will say that no, this is not the distance. How can I correlate in the year? At this for correlation, I require this. Similarly, over here, you see it is folded. So the distance, it is not this from this sample, ZX, and this is ZX plus H. No, if this is ZX plus H, so should I take from here to here? No. So it has to go like that. Suppose you see, you take the median line, put a thread, right? And you stretch the thread. That's the actual distance between this sample, that is what I'm calling as ZX, this one ZX, and this I'm calling as ZX plus H. That is the actual distance. What when you stretch this particular thread, median line, this is not the distance. So one has to be very careful when you construct semi-radiogram. It is not that many of us actually, we try to construct semi-radiogram without understanding whether the software is taking into account if the deposit is a folded deposit. Is the software capable of understanding the deposit is a folded deposit? You have to make the software understand. You have to write, if it is not incorporated in the software, you have to write in a small interface program by yourself and then make it interface with the software. Many times this doesn't happen. Most of the vendors also do like that. They don't explain because they themselves are not thorough about it. So use of software is another one thing. It has to be done very, very thoroughly. Many other time I've seen people are using software with the default values, and by the default values, you will not get the result. You will get a beautiful colored maps, but all those glitters are not gold. So you need to unfold if it is a folded deposit, right? There's a change in the dip, there's a change in the strike at dip, there's a swing, there's an embayment, there's a pinch and swell structure, there's folding of the mineralization needed because radiogram is best determined with a flat data set. So use of unfolding simplifies what is called domaining. This particular term I'll come later on. Domain, very, very important term. Okay. There are various models. And of those, all the models, 95% of our earth science application boils down to only one, that is called spherical model, right? And rest, right, 3% exponential and linear, but there could be a combination of, that is what we call the nested models. I'll show you some of those models. This is a spherical model equation, which is given by this particular, C0 is your negative effect, this continuity, this particular model equation goes by 3/2. That means basically it is 1.5 h by a minus half, that is 0.5 h cube by a cube. That is the model for all h being less than a. That means if this is my semi-variogram, for all values of, this is my range of influence, let us say a. So for all values of h, this is h less than a, this is h equal a, this is h greater than a. So till this one, h less than a, this will be the formula. The moment it reaches h is equal to a or h greater than a, that is why it is remaining flat, you will get this C0 plus C. That means, in other words, try to understand this particular component, which is called the growth rate of the growth of the curve, is defined by this particular function. This particular function gets a value of 1. You can say it for yourself when h is equal to a. If 1.5 h by a, h is equal to a. So this is cancels out, right? 1.5 minus 0.5, you get a value of 1. And beyond that, I'm restricting it. It will be this, whether it is h equaling or greater than. And of course, these two models are applicable for all. This particular two equations are for all models. As I told you, at h is equal to 0, gamma h is always equal to 0, and h tending to 0, that is what is called the negative. These two will be applicable for all models. But most of the time, I'll tell you, as the sir is telling, 95% of the situations goes to the spherical model equation. So I'll be confining to the equations. Other models, exponential model, it goes by this equations. The other two, as I said, gamma h, h tending to 0 is equal to C0, and gamma h is equal to 0 is equal to 0. Gamma h is equal to 0 is equal to 0. The same thing returns, but the main growth curve, this is the growth curve for the exponential model minus h by a, right? And there is another model which I've not named over here. It is called Gaussian model, which goes C0 plus C, 1 minus e to the power minus h square by a square. That is the model, Gaussian, right? Linear model, straight line equation. C0 is your negative effect, a is the slope. So this linear, this is a model without sill. There is no sill. Like in previous model, we have seen a sill. It grows, grows, grows. In some of the iron ore deposits also we have something. So this C0 is basically the intercept straight line equation, what you learned in our childhood days, in our school days. Y is equal to mx plus c, but we don't use this formula. We say y is equal to a0 plus ax. So that a0 is nothing but the C0, and plus ax, that a is the slope, so that ah.
Sarkar.
Yes, please.
No, I think we have a discussion part of it.
Yeah, we'll go to the discussion part. Let me just go through this part. This is one more very important part of it, because we cannot go to the discussion part unless the things are understood in its this one, applications and theory.
Thank you.
Right? Many of us do not know or are not aware of many of the terminologies. So discussions cannot take place without knowing the terminologies. So there are various types of kriging: block kriging, indicator kriging, probability kriging, universal kriging, co-kriging, and there are lots of other terminologies also. Co-kriging means kriging of one variable based on the other variable spatial coordination, right? So block kriging means kriging a particular volume. That is what we call block kriging. Point kriging is kriging a particular point which has not been sampled, right? Indicator kriging and probability kriging falls under what is called non-parametric kriging. That means we provide a non-parametric value over there. Suppose this particular grade, right, is I give a value something less than cutoff is 0, something more than cutoff is 1. So I get a binary distribution of the data and I carry out a kriging. That data is known as indicator kriging. Very, very useful. And one of the variant of this is called multiple indicator kriging, MIK. And a further, the assigning of the probability to each of these indicator values will be called as your probability kriging. So this is in a short. Now, if I give you a conceptual understanding of this particular block, which is being valued by two samples, one located at the center, another located at one of the corner. Let us say this block, I'm showing it to you in a 2-dimension. Let's say it is 3 meter by 3 meter block. One sample located at the center, S1, one sample located at this corner, S2. So, yes, obviously from the configuration of the samples, you will say that since it is located at the center, the sample S1 will be having a higher weightage, A1 weightage, S2 lesser weightage. And if I have a sample over here, again, a lesser weightage, S3, right? But then this will depend upon whether your semi-variogram was something like this or something like this, isotropic or anisotropic. Anisotropic means whichever the axis, it may not be only this, it could be this. So those are very important part of it, whatever it is. Now let us forget about those anisotropic or isotropic, will come automatically. Let's say the weights associated with S1 is A1 and with A2. Being known full that A1 will be much higher than A2 in terms of the weight coefficient. But this income, when you use ordinary kriging, the sum total of AI, that is sum total of all the weights must be 1. That is sum total of AI minus 1 is equal to 0. This is the constraint. That means we provide a value to the block based on the surrounding values or the neighboring values whose weights are assigned according to the distance of separation or the distance of separation from the sample to the block, subject to AI is equal to summation of AI is equal to 1. Now, many of us know of this, what is kriging known as BLEU, best linear unbiased estimator. Why it is called best? Because of minimum estimation variance. Why it is called linear? Because of weighted arithmetic average. Why it is called unbiased? Since the weights, all these weights sum to unity, that is equal to 1, which I mentioned now. And E of course stands for estimator. I don't want to go into those details of the mathematics jargons, but just to show you how the derivatives come. So this is what is the kriging variance, sigma square k. This is a computation of the semi-variogram kriging, right? So all that you have seen now is simple. I mean, what way of explaining? I've taken a particular technique of kriging, what is called ordinary kriging. We call it when kriging without knowing the mean. This is what is called ordinary kriging. When you know the population mean, then that particular kriging technique, which will not have that particular constant sigma AI is equal to 1, is known as simple kriging. These two kriging, both are linear kriging. This is what the unknown, the sample site is X0, which has not been sampled, right? Being valued by 4 samples, X1, X2, X3, X4, with different weightages, lambda 1, lambda 2, lambda 3, lambda 4. So, then again, this is the zone of anisotropy, right? The such ellipsoid. And I say that block is to be evaluated by how many samples? So what is the range of the sample? What is the range of the semi-variogram along east-west, along north-south? Can I stretch it further? If I do so, how many holes should be taken into account for the estimating this block? Again, a very, very important considerations to be taken into account for during kriging. So decision on the choice, this is another important thing. When you make kriging, when you compute kriging, let's say block kriging, what should be the dimension of the block? This is a very important question. I mean, not only in terms of our geology, but I'm talking about in the general mathematics. What should be the size of the domain? So this choice of a block, or in other words, selective mining unit, depends on various factors: sampling density, geological structure, precision of sample data, proposed method of mining, equipment capabilities, production target, desired use of the block, capability of manipulating use. But please remember, these are only few. I've not named all. There are many other factors. All have to be. But a thumb rule plays, we take 1/4 of the average sample spacing as your block dimension, right? Ideally, height of the block should be taken as that of the proposed mining height. The other two dimensions should equal at least 1/4 of the average drill spacing. It's very, you see, very fundamentally, you must understand, if this is my sample S1, this is my sample S2, how many points can I make over here estimates? If I place them very closely with each other, makes, let's say, another 100 points to be estimated, most probably there will be similar values coming up. It will not make any sense, right? So this is what I can take maximum, what I'm trying to say over here, 1/4 of the drill spacing. So this is one, right? This is another block. This is another block. This is another block. So mix up 4 blocks along the lateral dimensions. Okay. One of the most important component over here. Can you tell me, many of us, that is what Dr. Raju, let me tell you now, without understanding, suppose if your original frequency distribution goes something like this, can you tell me what is the mean of this data? This is fx frequency and this is x. People do not know what is called a frequency distribution. You will take it simply as x bar is equal to 1/n sigma xi. Do you know what is this going to give us? A mean over here. Do you know what does this mean? It is irrelevant. Absolutely no meaning. Abani, am I correct? Abani, are you there?
Yeah. Yes, you are very much true.
Yeah, I'm here, sir. Yeah.
Right.
Yes.
So this means this has got no meaning at mean. This is population component A, this is population component B. So you have new A and new B, mean A, mean B. So now if there is a mixture of the component, if you have taken samples from, so let's say, oxide phases and the sulfide phases, mix them together, you do not know the source of the data. And you try to compute your average like this. And then you try to blame statistics or geostatistics. Are you doing justice to the technique that you're using? So these are the preliminaries which you must know. These are called basically mixing of populations should not be there. Right? So in order to, geostatistical modeling, if carried out on mixed population, will yield only, it will yield incorrect estimates. You will never ever get, you will get an estimate. But whether that estimate is adequate, correct, you know the best result. Right? Before calling that geostatistics does not give you result. In case a probability plot that provides the number of population components reveals a mixed population, a split of the composite value database should be invariably be carried out with the aid of the geological controls, because it is the geology which controls or governs the mineralization phenomenon, not the mathematics. So these are some like this. When you want to make an outline of the body, right? So we say the blocks must be of uniform dimensions. So this is how the blocks are being, this is a mineralized envelope, have been computed. You can see the block dimensions. This Z means Z increment, X increment, Y increment, and the center is given. This every block is denoted by its coordinate as X center, Y center, Z center. Like you have multiple of blocks. I'll show you over here. Multiple of blocks. Look at this. This is the case of a mine in Sweden. Now, initially, you see, geology is not that straightforward. As you people are senior to me, many of you will be knowing. So it's simply getting the intersection in the drill hole and you make an interpretation, but the actual interpretation was this. So it is the same one now. Tell me, if you are getting this sample over here and this sample over here, and you are trying to compute a semi-program like this, will you ever get a good result throughout applying kriging? Never. So the
Sir, can we start discussion, sir?
We'll start, please. Please hold on. These things are very important. Then only this, you cannot come to this discussion unless I explain all these things. Am I correct, Sujit? So these are the most important parts. And now I'm coming to the important parts and applications. These are the blocks. These are the blocks of a bauxite deposit. 3D creek blocks. But to me, it doesn't make any sense unless I have a stacked blocks slice by slice. I'll show you that slice. Now, this is another dimensioning a block is very important factor. If you have a larger block size, you get a frequency distribution like this. If you have a smaller block size, you get a frequency distribution like this for the same property. Now look at this diagram and you put a cutoff. You get this much of misproportion. You get this much of ore if it is a smaller block dimension. If it is a bigger dimension, you don't get this much. So where does it go? Does it vanishing? It's cut off. When you apply a cutoff, it's known as a vanishing tonnages. This is a vertical stack which makes sense. This is what is called grade tonnage relationships. This was my original, my PhD time, that particular flow diagram. This is what optimization of exploration drilling. This I'll keep it open for discussion. Misclassified tonnages. Again, I'll keep it open for discussion. I'll not say it. Just show you. I've shown you one envelope, and I'll show you another envelope over here. Which is correct? I mean, which one should be accepted? This ellipse or this ellipse? And so much so, this ellipse turns to be a circle. Then what happens? There'll be no correlation between the estimated block values and the actual block values. So we say poor estimates. So when you have a tight ellipse, we have what is called your a good estimate, bad estimate, and a good estimate. Then in geostatistical grade control in mining, because in what happens over here, to maintain the grade consistency, it is required that the design of the blocks, mine layout, face advance, and bench progress should be such that overall variation of the grade is minimized in the direction of mining advance. And this is only possible by computation of semi-variables in various directions. Okay, so I'm not going to the simulation, excepting saying that the difference between estimation and simulation is that estimation provides only one realization of the true phenomena, whereas simulation provides infinite number of realizations, whatever method you adopt, right? So this is one example of our ordinary kriging using kriging, and this is sequential Gaussian simulation for the same property, and this is the original FE values. This is what a schematic diagram of a neural network model. This has got 4-layer model: input, output, pattern, summation. Input and output, that particular coincidence or correlation must be there. And through that, we have designed this particular model, neural network model, which is called a hybrid model. That means I've applied ordinary kriging, I've applied neural network, and particular technique that I've used of a neural network was generalized regression neural network, GRNN. This is a particular diagram. This is the first one is the ordinary kriging, and this is what is called the GRNN estimates, generalized regression neural network. These very things I was trying to tell you something about screen effect, outliers, increasing nugget effect. I was trying to tell you these are very, very important. Conditional bias, smoothing. These two things are basically called kriging oxymoron. You try to decrease one, the other will increase. Right? So you have to take care of both. Then screen effect. I'll show you in one of my diagrams. Screen effect. Let's say this is a block to be estimated by this few drill holes, by few the samples. This is falling on the same line. Screening off. So sometime let us use that value of this G1, G2, and G3. Let us say that they are 3 grams per ton, and G4 over here it is 1 gram per ton. Obviously, whenever you make any special technique, whenever you get a special technique, you will say that the value must lie between 3 grams per ton to 1 gram per ton. See what has happened because of the screening effect. The value has come out as 3.2 gram per ton. Will you accept? The value has come out as over here as minus 6.4 gram per ton. The value has come over as minus 26. These are all due to the screening effect. And you get a negative kriging variance. This is what I was telling you right initially. As you go on increasing your nugget effect, see the impact of the those weights of the samples given on my left-hand side. This is what is called the conditional bias, right? So these few things, mineral resource and reserve assessment without adequate geological input, could prove to be disastrous and constitute a critical risk. A robust geological model is therefore a prerequisite, and if the geostatistical model does not agree with the geological model, there are grounds for serious concern. Either one or both models should be critically re-examined and so as to establish the essential correlation and validation. So this research new techniques and applications, but validate new techniques adequately by following up or checking to confirm the absence of biases and the practical advantages to be gained when they are applied in practice. Now with this, I'll just come out with few things. Some universities, some of the training centers where geostatistics is being taught using commercially available software, with emphasis being more onto the use of software rather than the geostatistics domain knowledge, black box approach. This is where I disagree. From 1960 to present, two key issues that influence the progress of geostatistics and mineral industry: clarification and dissemination of geostatistical concepts and theories to the practitioners, identification and definition of unsolved problems in evolving geomathematical modeling techniques. It may be emphasized that deposit geology, suitably integrated with appropriate geostatistical procedure, provides an improved understanding of the mineralization types and specifics. So these are some of the conditions one must follow. Right? Acceptability in government agencies, I did not name to you. You know yourself how many companies are using government agencies as well as the PSUs and the private industries. These are some of the useful book reference that are of interest. Right? I've given you a list over here. Okay. One of the books happens to be from mine, Professor Dr. Gandhi and myself, 2016. And let me tell you, Abani was one of the reviewer of my book. That was in 2015. Do you remember Abani? So these are some of the books that are of use to that. Some of the softwares, commercially and public domain softwares, are listed over here, right? So like Geoscientists software, Datamine software, SARPAC, GEMCOM, Vulcan, Rockware, Leapfrog. I normally use Leapfrog software a lot, not Datamine, SARPAC, and GEMCOM. Every of this has got a lot of difference. Queries, please, for discussion. Yes, Sriji, please tell me.
No, thank you very much, Dr. Sarkar. It's an extraordinary talk, and it shows your extraordinary passion for the subject. And what you tend to tell, we all understand that the time is very, very short for you. But the way you wanted to project the geostatistics and for the betterment of the geoscience, that is wonderful with your the unbound knowledge. So before that, we start our discussion. I would request
I have, as the president of the SGAT, one comment to make. Omkar Mohanty speaking.
Please, sir, please, sir.
Yes. The comment is, of course, this was a brilliant talk, Professor Sarkar. Congratulations. Unfortunately, what happens is the time right now is 7:47 and we started at 6:30. So it's 1 hour, 17 minutes. So the whole question is one has to be prepared, actually. It's a very nice talk. It's an extremely important talk. And probably in the area of geology mining, this is very, very important. I was finding a similarity between this and what we do in engineering, very similar also in the engineering fields and how to analyze data in a steel plant, for example. And if you go to Cambridge University, you would have 150 open source softwares already. So the whole question is time is the essence. So unfortunately, the space that we have here and the time which you have here to accommodate this talk is difficult. So I was therefore wondering, we should have a very different kind of format to accommodate talks like Professor Sarkar's, which would be extremely useful for the industry. But the format has to be different. So therefore, the format which we have chosen, there is a bit of mismatch. So therefore, now that it is 1 hour, 18 minutes gone, it is up to our members. We can have actually an extremely short discussion, because after all, I don't think we can go beyond 1.5 hours, because that is about all. People have come prepared for a certain time. So therefore 6:30, so we would go up to 8 o'clock, which means 12 minutes only. I therefore ask my colleague, Mr. Sujit Mohanty, to take it forward with only a few questions so that in 12 minutes we are all through. Otherwise, it will become extremely taxing on the people who have come prepared for 1 hour and they can't stay beyond 1.5 hours or so. So with that, I return to you, Sujit Babu.
Yeah, now the forum is open for all of us. So that since the time is very, very short. So now I would request our distinguished participants, somebody who is having this application part, I think they can also demonstrate something and they'll share their experience, the field experience. So anybody having that experience can share with us.
No, I saw Professor Ravani Samal from US.
Yes.
Yeah, he on the chat, he said that I have come prepared for the discussion. So Dr. Samal, why don't you actually take the lead and perhaps share some of your thoughts, and we'll come back, Professor Sarkar, to this kind of talk. We'll bring also a few industry people who are actually practicing this and provide the forum. SGAT must provide a forum for such discussions, because it is absolutely obvious that one can actually arrive at completely wrong decisions and conclusions if one is not careful and take precautionary measures mathematically, as Dr. Sarkar suggested. So, Dr. Sam, over to you, Dr. Sam.
Just a point, not mathematically, geomathematically.
Yeah, that's right. Yeah, that's right. Mathematically, we have to take it metallurgical, mathematically also, and so on. Yes, Dr. Sam.
Before I start, actually, Sarkar sir, namaste, and Mohanty sir, namaste, and a lot of people here. I wish I was there in Bhubaneswar. I'll just make a couple of comments. No questions, actually. Just to clarify, I know Sarkar sir, like you said, it's a right way. It's not the format mismatch. But a couple of comments to start from the end. On the software side, softwares do their jobs. Personally, I am involved sometimes to vet the software. That means validate the softwares. I have friendship with every software manufacturer today. I maintain that relationship. So as a peer, I vet them when the critical tool is developed. They put it for about a year or year and a half for testing. I'm one of the many people test it. Having said that, I would say the ISAT software that Sarkar sir mentioned is probably the commercially available pure geostatistical package. And I won't actually vouch for make a recommendation for you guys to actually make a purchase or something, but that is a purely geostatistical package. And this is based on the research done in the School of Mines, Paris. Okay, entirely based on that. I was first introduced in '97 when they were beginning to get commercialized in India, actually. And they're extraordinary. I'm using them for last 20 years or so. Extraordinary package, but purely geostatistical package. Like Sarkar sir said, you really have to have a strong background, understand the basics, then you use it. Like when I do conditional simulation, you know what you're doing. And there are many things Sarkar sir said, I wish I had a checkbox. You check them, say these are so much important. One of the things from my experience, like Sarkar sir said that, the iron ore, I was dealing with a copper deposit in Brazil about 10 years ago. And very similar geological problem, but the learning point from me there was how important it is. I think it comes back to Mohanty sir, Omkar Mohanty sir, and many senior people like here with management roles in your careers. How important it is for the management to let the geology do their job, not interfering on their own work. In this project, I'm forgetting forgetting the name of the copper project. It was a totally vein type copper. It's not a porphyry at all. The initial thought was it's a lithologically controlled deposit, but the the team was given about 12 years. Over the time, there are only 3 or 4 people stick. They did remain in the team. The rest of the people changed. But I really gave a lot of appreciation to the management that allowed the geologists to continue to understand it. So that when the project went from preliminary studies to like scoping study to feasibility study, and you can see how beautiful the work that was. I use that, that example sometimes, and they also published that in the journal Economic Geology, their work, part of the work. Poyo gold deposit, it's a copper deposit, POLO is the name of the deposit. And that deposit, that just shows that how important the geological interpretation is before you start the geostatistics. The last point I would make about the application of geostatistics are the rigor of geostatistics depends on what you're trying to do and what you are trying to accomplish. Ore waste misclassification is a daily thing for me. I look at, when I audit any deposit, any project or anything, that is a kind of consequence of how well the work was done. When you do the resource modeling at the planning stage, we don't leave it there. It's applied in the operational stage. The people from Tata Steel Pro, Hindustan Zinc, you guys know, I know that you guys use it, not just do it, use it. And we use it, other parts of the world, and in a rigorous way. But the rigor of like how detailed your analysis that you do before you do the kriging or conditional simulation, that also depends what you want to actually accomplish. For an example, if you're at an exploration project, you just have 20-30 holes in a very large project, your data may not be valid to do the geostatistics. Goes to a project at the PFS stage, pre-feasibility stage. It's a whole different discussion to have what the stages mean, what the studies mean, and this all relates to actually what is the study definition as per JORC, EMIC, and NI 43101, like it course, right? The international definitions. When you end the PFS, the rigor that is applied to estimate the resources is substantially different, very detailed, and what we call local scale estimation is done well. I'm just simplifying the words, not using the jargons in a difficult to understand type words there. So at the exploration stage, the estimation may have a, let's say, you may have a chance of 40% or 50% chance of success. That means project may fail. That's okay. But when you going to the PFS, end of the PFS, going to feasibility study, just before the construction happens, before the capex is going, to make sure the estimations are good. I'm underlining the word. Make sure the estimations are done well. So that time we're looking at local scale accuracy. That means my own standard is 90-95% confidence interval. We have hardly 15%, or maybe depending on the type of commodity we're dealing with. Gold, copper, I do not actually, let the projects pass, beyond 10-15% variation. But yeah, sometimes iron ore, 20% variation, and iron ore doesn't go that far. It is very tight. So that's all the comments I have.
Thank you.
Thank you so much. Again, it was a learning opportunity for me.
I think now that because we are close to the time limit, which I had mentioned, and this is such an important topic. Actually, one could have a full workshop, and I'm actually thinking of having a workshop primarily on this, because this would essentially show to the state governments, to companies such as Tata Steel, where I spent 11 years of my life, how important many of these would be. So with that, I think I will only speak for 2 minutes and then bring it to a close. Professor Sarkar, we will have you once again, along with all our colleagues who are the practicing geologists from the companies, from the states, from everywhere else, because this is very important. And because this is just the opening talk, and I'm very grateful to Professor Sarkar that he agreed actually to deliver this, because all of us who have been teachers, we essentially involve ourselves with the accuracy to precision And one could see that the passion, the emotion, and the mathematics, everything put together is what actually describes Dr. Sarkar's talk today. So thank you very much, Dr. Sarkar. But what about SGAT and the fraternity program? Now, there are certain etymological differences between what Mr. Jadavananda Das said about our distinguished lecture series. You would very carefully see, actually, it is all within our members, that distinguished lecture series. So we have avoided the word lecture here, deliberately avoided the word distinguished. I know everybody is distinguished here because in your own professional way, you are all. And it's not exactly a series. It's a fraternity program, presentation program. Essentially, it means SGAT has provided a platform in which all of us, we have formed a fraternity. We have formed a platform where essentially extremely important items could be discussed, decided. That is the main purpose. And I think to that extent, I would like to thank also my friend, Mr. Jadavananda Das, that you have brought the right person to begin with. At the very least, Professor Sarkar, what it has done is your talk, it has probably energized the brains of many people. I could see about 62 people who were present at the beginning. And that's actually tells how important this topic is and how important the name is, that people know about Professor Sarkar. With that, I think we would close today's lecture. And I would ask, I don't know, Jadavananda Das ji or Sujit Babu, who delivers the vote of thanks.
Thank you, sir. Actually, you have already spoken about the idea and objective behind this fraternity program. And in fact, we thought of initially there are a couple of members from SGAT who wanted to join from the Tata and from Adani. They wanted to give their practical experience, but unfortunately at the last moment, they couldn't join. But we hope that in our next meeting, we will have a similar discussion where more than one speaker would be there. And what we are trying to do is a main speaker and along with the team speaker, and we will choose a subject and discuss. With this, I'll...
Actually, we had Dr. Samal also, in a way, contributed also a great deal to his experience. So we will try to format and keep things better.
So I thank on behalf of me and on behalf of SGAT to Professor Sarkar for giving us that extraordinary lecture. And as our president said, he has actually simulated our thinking process, that we have to be very, very careful and very, very involved in such reserve estimation. I thank our president, who in fact I thought about this program, and this is his grandchild. So thank you very much, sir. And we hope in our next meeting it will be much more participating. And
Thank you. Namaskar to everyone.
Yes, sir. I also thank our Vice President, Sujit Mahanti. He is also very, very involved right from the beginning. So I thank one and all, and have a wonderful time, and good night to all.
Thank you. Thank you very much. Good night.
Thank you.
Bye-bye. Happy Dasara to all of you.
Sir, happy Dasara, sir.